says click word. It doesn't really click or the click. Yes, we have a two decompositions here after that explanation.
Thank you very much. First, I want to thank the organizers for the opportunity to speak in this wonderful conference. So my first intention was to speak a bit about the previous convolutions via matrix subordination. But I mean, there are some key words here. I mean, free here means a new notion of independence, and I want to tell you what this is about. And yeah, of course, this is going to work with probabilistic and differential from CIMAT. But the thing is that maybe this is too specialized, and I will be quite happy if I can tell you something about pre-convolution, so maybe with the key, and a bit about the analytic subordination. And since we are in a Mexico-Poland conference, I would like to choose an approach which uses some contributions by Polish mathematicians, namely by Vargas Obieta and Prof. Lévy. I will write it down. Okay, so there will be some, so I will choose this approach, which is non-standard, but it's a very combinatorial approach, which I very much like to address this problem of subordination in non-commutative probability. So first, maybe talk a bit about non-commutative probability. So free probability is a part of non-commutative probability. So the main object in non-commutative probability is a pair. So we will have an algebra and a linear functional. So A is a star algebra, meaning that we have an involution. So for instance, for the algebra of complex random variables, we can choose the complex conjugation. This is an involution. For the algebra of, for instance, complex matrices, we can choose Hermitian transposition of a matrix. These are possibilities. With unit. And we want tau to be a linear functional. So from A to the complex number, such that it is unitary. Unitary linear function. Okay? So this pair, we will call it a non-commutative probability space. And the reason why we call this is because the main examples, I will jump directly to the examples.
What is unitary, sorry?
Unitary, this means that this has a unit with respect to the multiplication in the algebra.
No, but the functional.
Sorry, the functional. This means that, okay, with respect to this multiplicative unit, that this gives 1. Okay? And the thing is that we will use some tools from functional analysis, namely the Riesz representation theorem. And then, well, we sometimes also ask this functional to be positive. Maybe I will ask it already. And for this I mean that for any element of the form B star in my algebra A, then this functional needs to be take some value greater than 0. Okay, and the reason for this is that if we have algebras and linear functionals, we can use Riesz representation theorem to obtain probability measures from these. Measures. And if we also have unitarity and positivity, this makes the sign measures actually measures, and unitarity makes them probability measures. So this is why we ask these properties. And well, the main examples are two examples today. So one is I will have some algebra, I will call it AF, and then here tau will be just the usual expectation. And this, I mean, in the context of a usual classical non-commutative probability space, a classical probability space, namely a triple omega with a sigma algebra and then a probability measure. So I can consider this algebra to be in this underlying space, I can consider algebra of, say, bounded, complex, F measurable random variables, and then the expectation can be just the usual expectation, right? And then the structure is given by conjugation, so this is an example. And the second example is matrices. So I consider complex matrices, deterministic matrices, size n by n, and then I consider as my functional the normalized trace. So I normalize it to obtain probability measures.
Both ends are capital matrices.
Okay. So then, what is the general idea of non-commutative probability? Well, the main thing is that, I will try to convince you that we can say quite a lot about classical probability by reducing this structure and forgetting about the underlying probability space. So just by knowing the moments and the algebraic structure of our algebra of random variables, we can already say a lot. And the main idea is to try to use this abstract formulation of probability to try to then twist it a bit, and then try to find some algebraic structures which are relevant in classical probability space, in classical probability, to try to find similar structures somewhere else in mathematics. So one of the prominent examples of this is namely random matrices. Random matrices and freeness. Maybe large random matrices and freeness. So this is a prominent example of what I just told you. So Bojdecki in 91. So Bojdecki observed that one can formulate some definition similar to independence, which he called free independence, which actually describes the collective behavior of large matrices. And this was quite important for some problems in random matrices, especially when we try to compute global eigenvalue distributions. These have been quite effective. Yes?
This is not example 3. This is introduction, right?
Yes. No. This is one of the main motivations. One of the main motivations that So the main idea, the main ingredient is that we want to then, using the expectation, we can describe, for instance, independence. This is very simple. It's just that the moments factorize, right? So if we add just in this setting, then maybe we can twist the definition of independence and then maybe try to formulate some other sort of factorization. And then what Bojdecki showed that he proposed one of such twisted factorization that he showed that actually this notion of independence describes the collective behavior of large matrices. So I will be on this a bit later. Okay, but this is one of the main motivations. Okay, so these are two examples.
Maybe you can say what is a random variable in this context.
Oh yes. So since we are, this is one of the motivating examples. This example motivates all the terminology that we are using. And the main idea is that we can also then try to do the same thing, but in this sort of spaces where, there's no randomness here. Here we're just working with matrices, right? So, so that's the general idea. And then, well, in such a context, so we want to start talking about in this probabilistic language. So this, if we have a tuple A1, A2, A3, AK, a tuple in our algebra, then we call this, each one of these we call them non-commutative random variables. So this is a tuple of non-commutative random variables. And then to all the possible evaluations of our functional tau on products of these variables, we call this the moment, right? So we take tau of I1, I2, right? IM, and this is for all m greater than 1, and for all tuples I1 up to I. M less than k. So these are called the mixed moments of the tuple. So if A is this tuple, then these are the mixed moments. And then the distribution is just this collection of moments. Okay, this is what we call the non-commutative distribution of a tuple of random variables. Then of course, since we have a star structure, we have, yes?
By random variable will be just an element of the algebra.
Yes, it's just an element. So then the idea is that there are special elements. So we can consider, for instance, self-adjoint. So maybe more generally, normal elements. These are elements such that A star is equal to A star A, so they commute with their adjoint. So then in this case, of course, the collection of mixed moments can be collapsed, right? I mean, we only need to consider moments of the form A to the 1 to the power L times A star to the power M, right? So for normal elements, sometimes we may associate with normal elements, we may associate a probability measure which satisfies that tau of A to the L, A star to the M equals the integral of z to the L, z bar to the M, d mu of A. Right? So if we have this commutativity property, then all the information about the mixed moments can be contained in this kind of moments. And then we would like to have this situation. Okay? And actually, if we add some additional properties to the algebra, I mean, if A is a C-star algebra, then we can always find this kind of probability measures. Okay? So, but normally we will be having situations where these variables actually do not commute, and then the main thing we can talk about is this algebraic distribution, which is the collection of mixed moments. Okay? All right. So, of course, there are some other special situations of normal elements. Let me. What can I read? Yeah, maybe here. So there are special cases. So A can be self-adjoint, for instance, A star equals A. And then this means that the mu A is supported on the real line. Supported on R. Also another possibility is that A is a unitary element in the algebra. And that, so this means that A star, so that A is invertible and actually A star is equal to A minus 1. And then this means that mu A will be supported on the unit circle. And what else? Also, A can be positive. So A may be of the form B star for some other element in the algebra. And then this means that mu A will be supported on R star. Okay, so these are nice properties of elements. And then, well, I want to move quickly to this example. So we consider now matrices with respect to the normalized traces, and if we are in any of these situations where our matrices are normal, then the moments with respect to this trace, so the normalized traces of powers of a matrix which is normal will be exactly the moments of the probability measure. So if we have some matrix A in this space, we will send it to the probability measure. So mu A will be its moments will coincide with the moments of the probability measure, which is uniform on the eigenvalues of. So the uniform spectral measure of A, to say. So delta on lambda I of A, where these are the eigenvalues of A. Okay, so this is really nice. I mean, if we're in this example, then these are exactly the moments of the random variables that we know them in probability theory. And if we're in this other algebraic example, then we relate to any normal element, we associate this spectral measure. Okay, so these are the main examples. And okay, so what do I want to say now? Yeah, so since we only have this structure, we can only talk about moments and the algebraic structure of our algebra. We may want to encode our information in a better way. So maybe many moments are not so good of a choice. So let me erase this. So a better choice to have a very friendly approach to non-commutative probability is to consider the cumulants. And these pictures that I draw there are to introduce these combinatorial objects. So, moments versus cumulants. So the main idea is the following. So, of course, in classical probability we know that for many interesting probability measures, the moments characterize these measures. And we also, for a large class of random variables, the moments also characterize their joint distribution, and we can tell if they're independent or not, if these relations between the moments hold or not. Right? So the main idea to introduce this combinatorial object is to define the cumulants. So let me tell you what the cumulants are. These are just polynomials of the moments. So I define them recursively in the following way. So you consider, suppose that we have such a tuple of random variables. So the cumulants of A, so A in this context, this is a tuple of random variables, are defined recursively via the following moment cumulant formula. Which is the following. So I consider tau of A I1, A I2, A IM is really just the sum over all partitions in Tm of the cumulant indexed by this partition evaluated in A I1, A I2, A IM. And here I'm introducing how do you compute this kind of if you have a multiplicative function, if you have a sequence of functions, of functionals, multilinear functionals from your algebra to the complex numbers. So here I'm telling you how you do this. So let's do the first cases, right? So maybe
this is a definition of the right-hand side.
This is the definition of the right-hand side, yes. But it has to be done recursively. Okay, so let's do this first for m equals 1. Okay? But maybe let me just explain you what are these partitions, right? So P of 1 is just, it only has a single element, so it's a set of identity 1. So P of 2 is all the possibilities of partitioning the set of two elements into blocks. Right? So I can either have the two elements in different blocks or the two elements in a single block. And then the partitions of three elements, I have 5 elements, right? So I have this guy, everything in the same block. I have these other guys. And I have the one with all the points separate, right? So in this way, I can define P of n, right? It's just the way of partitioning my set of n elements. And then I have other sets. I have the non-crossing partitions and I have the interval partitions. So the interval partitions do not allow me to have nestings. So a block cannot be nested inside another block. Okay? So this is why I write that the interval partitions, if I add this nesting block, then I get the non-crossing partition and the full set of partitions. And then the non-crossing partitions, I do not allow this kind of behavior. Okay? So this is the difference between the different lattices of partitions. And then in general, I have that this is contained in this and in this. Right? Only for the first cases they coincide. But then for the first cases, so here I'm only using the partitions, right? So for now it's only, yes?
Interval partitions are what?
Or interval partitions, I do not allow this one. So I do not allow nestings of blocks.
For crossings?
Yeah, crossings either. I mean.
So every block is an interval?
Yes. So interval partitions can only be something like this, right? Okay, so let's calculate the first cumulant. So for the first cumulant, I will have one partition. So I have the tau of A is simply the first cumulant. So this defines me my first cumulant. Right? So I actually want to define these Fn's. I want to define the Kn's. Right? So K1 is simply the expectation. Now what happens with m equals to 2? So I have that tau of I1, I2. So this gives me the sum over these cumulants. So I have the cumulant associated to this guy applied to AI1, AI2, plus the cumulant associated to this partition of AI1, AI2. Right? And I mean this guy, I define the cumulant of the full block to be this Kn. Right? This is my convention. And then I only want to define it recursively by using this way of partitioning the blocks. Okay, so what does this tell me? So I want to define this K2, right? So I have to solve this equation. But then I already know what is the value of this, right? Because if I have some partition, then f pi is just evaluating my functions on the arguments according to the partition, right? So here I have A1, A4, and A6 in the first block. So I have them here in the arguments. Maybe it's easier to go from inside out to outside. Right? So I have here this A5 along, so I calculate F1 of A. Right? I have this block here, so I calculate this F2. So it's just the way you have to evaluate these maps. Okay? So then in this case, I know that this is just the product of the first cumulant evaluated in each one of these guys, and the first cumulant is just a mean. So I have here tau of AI1 times tau of AI2, right? And then if I solve, then I get that this cumulant that I want to compute right, it's just for this plus this guy, right? So this is just the covariance, right? Okay? the idea is that, well, maybe first just stick to classical cumulants first. So this is the covariance, right? So in particular, if my two random variables are independent, then if I evaluate the second cumulant in two independent random variables, I will get 0, right? So then the next thing is that, well, we can characterize independence in terms of mixed moments, and one can solve the moments from the cumulants. I mean, if you know all the mixed cumulants of your random variables, then you can solve the moments and get them. So you have exactly the same information. So there should be a way to translate independence in the right-hand side, right? And then there is this really beautiful theorem. So, I mean, we know that, okay, let's say A1, A2, A, are independent. This is if and only if, I mean, model of some properties on the distribution, but they are not so crazy. So this amounts to showing that the expectation of AI1 to the power K1, A2, K2, K, N1, N2, and K. So this has to be this problem, right? But then, I mean, of course, you can now translate this to cumulants, and this is if and only if all mixed cumulants vanish. Right? I mean, we know that having zero covariance doesn't mean independence. Right? You can be uncorrelated but not independent. So then this is exactly the generalization of the covariance that you require to characterize independence in this way, in our orthogonal relation. So by this I mean that, for instance, K2 of A1, A2 is 0, right? And this is equal to K3 of A1, A2, A1, right? Etc. Right? So of course this is an infinite system of equations, and this is again an infinite system of equations, right? So this is very nice because then, I mean, if we want to calculate cumulants of important random variables, let me see where I can. Okay, maybe we already know this, right?
How do you call that bands?
Sorry?
How do you call that bands? Do you have a name for that?
For which?
Fn.
Fn.
Yeah.
So I guess we call this a sequence of multilinear functionals, and then this F5 will be the multiplicative extension. So now, let me give you some cumulants of famous random variables. So, for instance, the central limit theorem, the law of large numbers. So here we consider the Sn to be the sum, normalized sum of n identically distributed random variables with the first moment, and so we know that Sn converts in distribution to its mean, right? X1, right? Xi are IID. So we know that the Sn converts in distribution to this random variable But then we can also calculate, so then we can calculate the cumulants of Sn, right? So the nth cumulant of, so what will happen with this cumulant? So cumulants are multilinear, so this is a proposition, so maybe a proposition cumulants are multilinear. And this follows just from the multilinearity of this expression, right? So then, since they are multilinear, I will have to only calculate so I will have some n to the power m minus 1. No, n to the power m, right? And then here, I will have the sum over all the possible cumulants on the x-side, right? Because I can expand this sum, right? But then all the mixed cumulants of the independent random variables vanish. So then, actually, here, I will only have, well, these sums, right? The km of the x1 plus km of x2, right? So I will only have n times the nth cumulant of x1. So this is why I put here minus 1. No, sorry, n to the minus m plus 1. And here I will have the cumulant of x1. Right? So if I make n go to infinity, this will be 0 if m is greater than 2, and this will be exactly the mean if m is equal to 1. Okay, so I have a very nice characterization of constant random variables. Of course, these are the simplest random variables, constants, and they satisfy that all the higher order cumulants vanish, and only the first cumulant is the mean. I mean, I already calculated that the first cumulant has to be the mean always, right? So this is very nice. I mean, the constant random variables have vanishing second order cumulants and so on. So then what's the next level of simplicity? I mean, this is also very nice. So now if I consider the central limit theorem, now I have this normalization, and now I ask the random variable to be centered, right? So E of x1 equals 0. So then I can use exactly the same argument, and now here I have m over 2, and then here again I have 0 because the means are all 0, so the mean of the sum is also 0. And then here I only have.
So you need to ask for finite variance.
Yes, sorry. And here I have. So this gives me the variance, right? And the rest gives me 0. So this is very nice because, I mean, if I go from moments to cumulants, then I have these very nice characterizations of these important random variables. And not only that, I mean, I can also ask for some other random variables. Maybe I do this here. So now if I consider the cumulants of a Poisson random variable, the kn of x, if x is Poisson, then this gives me a constant, the parameter lambda of the Poisson distribution. So this is also really nice, a really nice characterization. And now, what I want to do is, I mean, I introduced you these other combinatorial lattices, right? So what are these about? What are these for? So let me now, just as I defined the classical cumulants, so maybe I will go define the three cumulants first. So I only change from this formula that I will only be summing over the non-crossing partitions. It's the same formula, and this defines me recursively another sequence of cumulants, which are now indicated with an R. Okay. So then, I mean, of course, the first two situations are the same. So again, the first cumulant is the mean, the second cumulant, pre-cumulant is the covariance, so nothing changes there. But from the fourth cumulant on, then something else happened, right? So, I mean, I had this really nice theorem that the cumulants were characterizing independence, right? So now, of course, I'm defining some new polynomials. So this will not characterize independence anymore. But then I can define independence, a new notion of independence, by asking these cumulants to vanish, right? And of course, if I define this notion of independence by asking these cumulants to vanish, then I can also try to do a free central limit theorem and a free law of large numbers. And then of course, I mean, these proofs remain the same, because I only use this property of the cumulants being vanishing whenever I plot different variables, right? So then this is very interesting because, or maybe, yeah, maybe I will already say this. So if now you consider the free cumulants, okay. So if you now consider this kind of random variable such that only the second free cumulant is not vanishing, then the random variable has to be a semicircular distribution. Okay? So let me now introduce a few random matrix models. I will do it here. And I want to tell a bit about this result by Bojdecki in 91, where he related these two independence with this.
So you are defining new cumulants.
Yes.
From those R's.
Yes.
Okay, you need some natural properties of R's and then summing over crossing.
Yes, this is only replacement, and now of course these cumulants now mean something weird. We would like to see what they mean, right? At the moment we only know that the distribution which has cumulants 0, 1, 0, 0, 0, 0, 0, this is the standard semicircular distribution.
The relationship between cumulants and moment does not change. So what's as before?
Yes, the same. It's the same. The only change is the lattice that we use here. Same definition. Okay. So now some models from random matrices. So, well, our main object for this talk will be this matrix set n, which is 1 over square root of n, and then I have just set ij, and these set ij's are independent, identically distributed, complex normal, standard complex number entries. So then this is a very hard random matrix to deal with because this is not normal. But the first random matrices that were treated, I mean, in the sense of trying to deal with the eigenvalue distribution, were just modifications of this matrix. Namely, if you take, say, xn equals set n plus set n star over square root of 2. Then this is the so-called, this is one of the so-called Wigner matrices. And Wigner, in his pioneering work in asymptotic eigenvalue distributions in the 50s, he showed that the eigenvalue distribution, I mean the eigenvalues are random, and he showed that if you pick one of these eigenvalues at random, this has some density, and he showed that the distribution converges as n goes to infinity to a semicircular, to a semicircle, I mean, scale so that it has probability, it has mass 1, of course. Then, maybe a decade later, Marchenko-Pastur considered the Wishart ensemble. This was already considered by Wishart, but not the question of the eigenvalue distributions. Wishart considered some other properties of this ensemble. But then Marchenko-Pastur in the late 60s, he said 65, 67. He showed that in the same way, this is a positive definite matrix, random matrix, so the eigenvalues will be positive, and he computed this, which is now called the Markov-Pastur law. And moreover, they only not showed that this matrix model converges to this guy, but they also consider a more sophisticated problem where they put some other matrix in the middle, let's say a deterministic matrix, and well, they asked some property for this matrix. I mean, they asked that the asymptotic spectral distribution of this matrix should converge to something. So they asked, this can be algebraically, this amounts only to ask for these moments to converge to the moments of some probability measure, let's say mu d, right? And then they show that you can also compute this asymptotic distribution, and of course it will depend on it does not depend on the specific choice of your matrix here, it only depends on the spectral distribution. Okay? So these were the first matrix models which were investigated. And so now, I mean, I already told you that the analog of the Gaussian distribution in the free world is the semicircular distribution. Yes?
And now the function now is the expectation of a trace. Is that correct?
Yes, yes. Yes, yes. One very important property is that if we have A1, tau1, and A2, tau2, then A1 tensor A2 and tau1 tensor tau2, these are non-commutative probability spaces again. So actually, yes, the main example of non-commutative probability actually comes from combining these two basic examples which I introduced. Okay? How much time do I have?
Just 6 minutes.
6 minutes. Yeah. So not a convolution at all. Yeah, so then, what other property do I have? So I told you about the cumulants of the Poisson distribution. These are just lambda, the parameter of the Poisson. So actually, if you have the compound Poisson, so it satisfies. So for a compound Poisson, we have to. It requires a parameter, a probability measure, and the compound Poisson is the probability measure which has so its moments, no, its cumulants are the moments. So maybe let's call it pi or. The cumulants are the moments of this nu. So actually, in the free sense, this model studied by Markov-Pastur is the free compound Poisson. So this first model that they studied, I mean, this set n star. I mean, for the sum, it was important that these guys had the same dimension. But if I choose maybe this guy to be a square, a rectangular matrix, I can still consider set n times set n star. And then it turns that the free cumulants, so if I consider the free cumulants of this guy, well, I mean, I should put this in all the arguments, right? So the pre-cumulants of this guy are exactly just lambda. Where if my matrix now is size m times n, this lambda is the limit of n over n. Okay, so the Poisson, the free Poisson distribution, the analog of the Poisson distribution in the free world is this asymptotic spectral distribution of the Macheco-Pastur ensemble. And if you consider now this other case, if you put one D in the middle, then these are exactly the moments of D. Oh, I will put. Okay? So the model by Macheco-Pastur, when we insert one matrix in the middle, is exactly the analog of the compound Poisson. Yes, so I wanted to say much more. But then, I mean, maybe I will just end with Voiculescu's result very quickly. So we have seen some quite nice coincidences, right? Just by switching these combinatorial objects. But then it's not only about this individual behavior. I mean, here we're only talking about a single ensemble, and then try to describe the value distributions, right? But then, if we consider several of these type of ensembles, so Voiculescu 91. So if you consider this xn1, xn2, and let me just introduce another one. So if you consider xn times wn to the power 1 over 2 minus 1 over 2, this is a unitary matrix. Okay? So now suppose that you consider independent realizations of all of these random matrices, right? So you have several independent realizations of the linear matrices, and you may also have some of these guys, right? So this is U4 because this comes from some X4, right? And then so unitary matrices, and then maybe some Marchenko-Pastur matrix, Wn6. So here, I mean, the indices, I mean that I generate an independent one of the matrices, and I do this. So then what Voiculescu showed was that the moment with respect to this 1 over n, the expected trace, converge to free random variables, to free operators. Then we have some limit in x, x1, x2, x3, u1, u2, w1, for instance. And the relation between these guys is free. I mean, we already knew what is the distribution of these guys individually, but the collective behavior between them is freeness. So if we compute these mixed cumulants, they will vanish. And then this allows us to compute moments of combination of these kinds of matrices. And these have been quite successful for computing these global eigenvalue distributions. So I think that's it.
If there is some very, very quick question, then I can accept.
The only difference between the free cumulants and the original cumulants is that the setting which we are
adding the partitions is different.
Yes.
Instead of like adding over like all possible partitions, we're only adding on like the ones that are not crossing. Are there other sets that generate other sense of like independence or?
Yes. So this I also wrote the interval partitions. So this generates some other kind of independence.
And is there like any other one or?
There's a paper about this. I can give you the reference.
Thank you.
Okay, thank you.